Hello, everyone. My name is Igor Sveligoy, and I'm from the University of California, San Diego. And I'm going to present our talk about managing cloud networking costs for data-intensive applications by provisioning dedicated network links. Let me point out that this was a team effort with the most important players listed below: myself, Frank, Tom, Michael, David, Benedict, Steve, and Vladimir. It also involved several organizations, with the major one being UCSD, University of Wisconsin-Madison, and Internet2. Now, I hope everyone in the audience knows that commercial clouds these days can provide large amounts of compute capacity, and that operating in spot mode can make them almost reasonably priced. We had a related presentation last year at PEARC about that. However, for network-intensive applications, the cost can easily balloon since one has to pay for egress that is shipping results back to on-prem. Note that ingress is always free. One way to lower this cost is to provision dedicated network links, and that's what we did. One can have saves in between 50 and 75%, depending on how well you can use these links. And that's what we did. We were here to present our experience egressing about 130 terabytes in about half a day. Now, let me point out that this was just not a CS experiment, because while doing pure CS experiment is fun, demonstrating infrastructure capabilities while doing real science is even better. So we produced simulation data for the IceCube experiment, which is a large neutrino detector embedded in the ice at the South Pole. And here you see a nice picture depicting the detector and where it is located. We use the cloud instances from all three major cloud providers for the compute part, and then stored the results on-prem to locations at the UW-Madison and UC San Diego. So why do we need large-scale computing for IceCube? Well, the detector is built into a natural medium, so it is hard to properly calibrate. We drop the detector into a gray box, and the ice is very clear, but is it uniform? Has the construction changed the ice? And that's important to know, because you can have drastic changes in the construction position with different ice models. You had seen down there in the pictures what that looked like. Also, let me point out that the problem is too complex for a parameterized approach. So we pretty much have to brute force it using ray tracing on GPUs. Now, it's also worth pointing out that IceCube is used to distributed computing. Most of its compute resources come from the Open Science Grid, where HT Condor plays the workload management system role, and Grid FTP is the transfer mechanism. Here is a snapshot of the last year, and you see that they used about 9 million hours of GPU compute last year, which is quite a bit. Now, the Open Science Grid is indeed all on-prem, but it's globally distributed. So added cloud resources was quite trivial. Indeed, we presented doing that last year, adding a big chunk of cloud resources. What is different this time is that we wanted to support a data-heavy simulation workload. In particular, the chosen workload produced about 500 megabytes of data for every teraflop of hour of compute. And as you can see from the table below, the least price for egress can be comparable to the compute costs. Indeed, if you look down here, you can see that for T-Force in spot mode, the data transfer is actually quite higher than the cost of the compute, 16 cents versus 12 cents. So that's not something you want to see. It's like too bad that we could not get all the compute done on T-Force, which are really cost effective, but we want to go big, and there were not too many T-Force available. So we used all of those cloud GPUs. And you see some are really way more expensive than the others. But for most of them, the cost of networking can be quite comparable. So we decided to do a cloud burst using dedicated links. because we projected it would cut the cost of uh, egress to about a half, from 16 cents to 8 cents per job. Now, you do pay a fixed hourly cost to use these links, so you have to keep them busy in order to get the most cost benefit out of them. But it can be done. Fortunately, it gets complicated fast. IceCube storage can sync 100 gigabits per second. We knew we could get more than 80 gigabits per second to UW-Madison, and we had another 20 gigabytes per second, gigabits per second to UC San Diego. However, Internet 2, which is the peering point to the clouds, had at most 2 times 10 gigabit links to any point for Amazon and Google. The only bright exception were the California link to Azure, which was multi-100 gigabits, which was nice. And moreover, these links are shared, so you can never get the whole link to yourself. And on top of that, there are fixed limits of how much you can get out of them, which is 5 gigabits per second on Amazon and Google, and 10 gigabits per second on Azure. And you cannot just pick any random bandwidth limit. It's rigidly defined. It's either 1, 2, 5, or 10 gigabits per second. So to fill an almost empty 10 gigabits link, you actually need 3 links, 5 and 2 gigabit per second links. So we ended up with over 20 links in the end. Azure was okay, but we really need a lot of links to get all the bandwidth we could to Amazon and Google. And you see all the links there listed there in the table. Now, on top of that, you also have the problem that final users cannot provision dedicated links on their own. The process really involves 3 parties: the cloud user or the final user, the intermediate network provider, and the local on-prem networking team. So the human interaction really plays a significant role in establishing and tearing down of dedicated links. And because of this human interaction, it is virtually impossible to do full automation in most circumstances. Let's first look what is needed from the on-prem networking team point of view. They need to provide dedicated IPs to be used for the cloud compute instances. And it's often untrivial to get an IP allocation at any institution. We used private IPs, which are easier to get, but may not be an option in other use cases because they're not routable globally, but we just needed to stay within the institution, so that worked. Just to point out that IPv6 could be another option, but we did not go that part for several reasons that I will not discuss here. And once you have the IP range, you have to create a path to the peering point. And Internet 2 has several such points, as you can have seen on the table in the previous slide. Oopsie, how do I get back? Oh, here we go. See, we have several regions there. So UW and UCSD chose to go a slightly different route. The UW used the BGP-based layer 3 VPN to Internet 2 via their regional aggregator, which is Omnipop, while UCSD first provisioned a layer 2 VPN over the regional provider, which happens to be Scenic, and then layered on top of that a BGP-based level 2 VPN to Internet 2. So some work is needed there. At this point, you are ready to actually provision the links using the cloud portals. But how you do this is very different between the 3 cloud providers. AWS is hands down the more complex. You see how many steps you have to go through. And it's also the only cloud provider that requires the on-prem network engineer to initiate the request. The other 2 is the user that does it and then just passes over the activation keys to the other side. Of the other 2, Google is definitely the simplest. You see, just 3 simple steps. Azure is not much harder. Just be aware that Azure allows for a lot more customization. and you actually get what you pay. So be careful not to get the default cheaper solution, because you will not get much performance out of that. So in summary, provisioning and tearing down of dedicated network connections is hard. It involves many parties and many steps. So definitely not meant for frequent use. Once established, it actually works fine. So it works really well for long link deployments, but it's not so trivial when you want to do short cloud bursts. One has to see really how much is it saving to decide if it is worth or not. In our case, with 130 terabytes of data, we estimated that we would save over $5,000. So it was definitely worth it. But I would not recommend it for anything significantly smaller than that. Now, to the execution. Let me start by pointing out that IceCube workload was pretty much the worst you can deal with. Its network traffic was extremely spiky. All the data is transferred right after the compute is finished. So you have something like 20 minutes of compute followed by seconds of file transfer. Now, luckily, we are not dealing with single jobs, but large sets of jobs. So there is a chance to smooth that out on average, but that doesn't work if all jobs start at the same time. So we ran a test to see what would happen in the all jobs start together worst case scenario. And you see it gets messy. You either over provision and underutilize the links, like in the picture above, or you saturate the network link, and then essentially the file transfers start to take a long time, and you're wasting compute resources. Now, since we start with no compute resources and must actively provision them from the cloud providers, an easy way to spread out job startup is just pace the provisioning. And that's exactly what we did in our main cloud burst. We ramped up for about 2 hours until we reached about 80 petaflops worth of compute. We had a second bump later on, but that's just similar. As you can see on the snapshot of one of the network links, this allowed us to get the mostly smooth network utilization. So smoothing out can be done even in this very spiky workload. Now, things worked quite well on average, but remember, we used only spot instances where you never know how much of which resources you will be able to get. Someday you'll get more, someday you'll get less. And especially when you try to push the limits like we did, it's hard. Indeed, we hit the capacity limit of many resources in many regions, and of course, not all at the same time, which made it even more trickier. So we did saturate the networking on a couple of links, unfortunately, resulting in longer transfer time on those, as you can see on this other graph. But it's just a couple of them. Most of them were actually doing pretty well. So overall, it was quite a success. We produced a total of 130 terabytes of data, and they came in about 54,000 files. Most of them went to UW, while a fraction went to UCSD. And all that traffic to UW actually managed to almost saturate the wide area net research link that UW has to the wide area network. As you can see down here, we have peaks of 90 gigabits per second, and we stayed at around 80 gigabits per second for several hours. Now, it is not all our traffic, but that's what the link was seeing. So really, we have pushed what they could deliver. And just as a side note, it took about 225 petaflop hours of GPU compute to get all the data. As for the cost of the main run was $31,000, all included. And out of that 31,000, about 5,500 was spent networking. If you do the math, this comes down to about $42 per terabyte. And if you look at the list prices, if you went the regular path without dedicated links, we would have paid around 11,000. So we definitely seen 50% saving on network costs, which is about 20%, more than 10% of the total, which is not negligible. And this is all I have. So just to summarize, the cloud egress cost can be a substantial burden for data-intensive applications. But you can use dedicated link that provides saves between 50% to 75% of the network costs. We show that one can provision 100 gigabits per second in aggregate bandwidth through Internet 2, but we had to use many links. And capacity planning and workload steering can be a challenge. There is high networking provisioning overhead. And if you have spiky workload like the IceCube one, steering the workload can be challenging. But all in all, it was a success. We actually managed to produce lots of valuable science and get some decent savings in the process. Thank you. So just to acknowledge that this work was partially funded by the NSF through the following grants. Thank you.